let's try to make it interactive. And if you have any question, please feel free to interject and ask. And let's start. So this is the paper in collaboration with Alberto Bietti from Flatiron Institute and Gladio Dai and John Buna from NYU. So what we're trying to do. So we know that one of the basic abilities of language models is that they have very vast knowledge about factual information about the world. And people have tried to quantify this knowledge. So we know that the knowledge is somewhere in the parameters, but the question is where and in what format, so how the model is actually storing all this knowledge. So we try to understand how do transformer language models in particular memorize factual associations and what latent representations support the factual recall. So this is the roadmap for the talk. So I'm going to present some background on factual recall in language models. Then I'm going to present our main contribution, which is a geometric approach to factual recall in a toy simple model. Then we are going to see some experiments about whether this is something that is actually learned by models undergoing descent. And finally, I'm going to touch the question of whether we see some signatures of this solution in real language models. Okay, so let's start. So we know that one common way to model factual information is using this triplet of subject, relation, and attribute or answer. So for example, we can have the triplet, Marie Curie was born in Warsaw. So was born in is the relation that specifies the type of information, the type of relation between the attribute or the answer and the subject, Marie Curie. And of course, we can ask different questions about every person. So we can ask about the birthplace, the occupation, native language, etc. All of these correspond to different factual relations. And another basic property of factual knowledge is that we can compose questions into multi-out questions. So for example, we can ask, what is the mother of the wife of X? So we compose the relation wife of with the relation mother of. Okay, so one common account of factual recall and transformers following the work of Morgeva and others is this view that the feed-forward layers in transformer are where the knowledge is stored. So in generally, the two main models in transformer are the attention model and the MLP or feed-forward. And it's common to think about the feed-forward network as a kind of key-value memory map, where if we have some key that tries to retrieve some information, like Marie Curie was born in, we get some query vector in the middle layer of the MLP, and the second layer of the MLP retrieves the particular answer for this query from the parametric knowledge that is stored in the parameters of the language model. There are attempts to formalize this account. So, and one very basic attempt is this view of associative memory. So if we have a set of vectors x, x1 to xn, and we want each x to be associated with some y, which is the answer, so y1 to yn, we can compose this very simple memory matrix where w, which is just like the sum of the outer products between each key and value, each x and y. And because of like very basic properties of high dimensional vectors, the interference is very small if the dimensionality is high enough, so the vectors are roughly orthogonal. And once we computed this memory matrix, we can take the matrix vector product with a particular x, and we are going to get as an answer the particular y of this vector. Any questions so far? Okay, so if there are no questions, I will continue. So notice that a particular assumption here is that the embeddings are unstructured. So usually we model them as a unit vector on some like high dimensional sphere. And there are attempts to actually like calculate the capacity of such constructions. both in this like linear structure and in like actual MLPs that approximate this linear associative memory. And the finding is that the capacity is roughly linear in terms of the total number of facts, which is n, the number of entities or subjects, times r, which is the number of factual relations. And you can see it in the plots below that empirically, if you train models on this kind of like synthetic data set of n entities and r relations, you indeed see a linear relationship between the capacity and the dimension of the model. Okay, so that's nice. So parameters count scales linearly with the number of facts, but this assumes two things. So first, they assume disjoint attribute sets per relation. So the sets of attributes or answers are disjoint between different relations. And more importantly, the embeddings are assumed to be random and fixed through training. So we don't have any learned representations of the entities that we are going to memorize. Each entity just like gets a random embedded. Now, of course, like this diverges from what we have in real models where we learn representations of each entity. So the question is whether we can do better using trainable embeddings, and what is going to be the solution. So what kind of embedding we should learn for the entities for in order to have optimal factual recall. So this is just like some motivation why we need why it's worth it to analyze the case of learned embedding. So as I mentioned, like this is what we have in practice. We have an embedding matrix that is trainable. There are some accounts recently that like geometric memorization is important. So models do use the representations to memorize better. And one important empirical observation that I will go back to later is this finding about linearity of relation decoding. So people have observed that empirically, if you take a pre-trained language model, you can fit a linear map that maps between the representation of the subject or the entity that we want to ask something about and the answer or the attribute. So in the example before, we have a linear map between the representation of Marie Curie and her occupation, for example. So this is something that people have observed empirically, but we do not have a theoretical account that explains why this is the case. So empirically, embeddings are correlated. They are not nearly orthogonal. And our goal of this in this paper is to propose one possible account for this situation with trainable embeddings. Any questions so far? Okay. So in particular, we're going to try to answer the following questions. So first, can learnable embeddings reduce the embedding dimensions to something logarithmic in the number of entities without inflating the other parameters of the network, which is the MLP or the attention? We're going to try to understand what is the solution that gradient descent is actually converging to, and whether it resembles the classical solution with random embeddings and the parameters of the MLP serving as memory, or whether we're going to get something else. We're going to put particular attention into multi-hop questions and multi-hop questions and understand whether the geometric solution with learned embeddings proposes a favorable properties in this case. And finally, whether we are going to see something like this in real language models. Okay, so in terms of the like high-level contribution, which I'm going to delve into very shortly. So first, we are going to show that if you train the embeddings, you have what we call logarithmic memorization. So we can have relatively small embeddings, linear in the number of relations, but logarithmic in the number of entities. And usually the number of entities n is much larger than r, the number of relations. And we're going to show that there is a solution where the subject representation, the embeddings of the subjects, are some kind of like linear superposition of all possible attributes under all possible relations. And in this solution, the MLP does not actually store information. It doesn't serve as a memory. It just like selects the relevant relation from the embeddings of the subject. Finally, we are going to analyze the capacity depth trade-off in multi-hop factual recall, and we're going to show that without chain of thought, you need a relatively large MLP, linear in the number of facts, or very large embedding vectors. But with chain of thought, we are going to get a linear solution in the number of relations. So chain of thought makes multi-hop factual recall much more efficient. Okay, so let's start with the toy model that analyzes the trainable embedding solution. So the task is the following. We have n subjects, R relations. So each relation R has some ground truth bijection function GR, which maps any of the possible n's to some other n. So for example, if the particular S is Marie Curie, we have a relation R for the birthplace and some other relation R prime for the occupation, etc. And each relation in our assumption is a bijection, which maps to some other subject in the vocabulary. And in general, the training sequence in autoregressive language modeling is going to be this vector X, which is some subject, following by K relations that we have to compose, for example, the mother of the wife of someone. And the final answer Y is going to be the composition of this set of K relations. So the simple case of a single op relation where K equals 1, the sequence is just going to be S, R, and then the model has to complete G of R, which is the answer under this particular relation R. So we assume that attributes come from a shared pool, so it's somewhat more challenging setting than the one analyzed in previous work. Is it clear overall, like the structure of the training sequence? Okay. Now, given this data distribution, we are going to analyze roughly standard transformer. So it's going to have either one or like more than one relations, but more than one layers. We're going to have a uniform attention. So we're going to assume this like simplifying assumption that the attention model is fixed to be uniform. We have importantly learnable or trainable embeddings x1 to xn. And we train the model as an autoregressive language model. So we treat the subject representation, then the representation of the K relations, and it has to complete the answer embedded. Okay, so the only important change is that we have trainable and not fixed embeddings. Okay, so now I'm going to start with covering the theoretical findings. So the basic finding is if we focus at first in the single op case, so K equals 1, we just have a single relation. Then we have the finding that a one-layer transformer with relatively small MLP, whose width is just R, so it doesn't depend on the number of, or like it depends logarithmically on the number of entities n and not linearly, is enough to store n entities and R relations. So the dimensionality of the embeddings is going to be R log n. And this solves all single op factual recall questions on this set of entities. So the important thing here is that the MLP width is independent, or at least not linear in n. And not that this contrasts with what I showed earlier about the case of random embeddings, where we need relatively large MLP, right? Linear in the number of facts, so linear in n and in r. So the total parameter count is the same in both solutions, and this is not coincidence. Actually, like this is like the lower bound of the number of parameters that we are going to need. But note that here in this solution, most of the facts are stored in the lookup embeddings and not in the MLP. And this is just like much more efficient in modern architecture. So we have like a direct access to the embedding of a particular entity, and it's much more efficient than storing the information in the MOP parameters. Any question? Okay. So what is the construction? So as I mentioned previously, we can have this very simple structure where the embedding of a particular entity or subject S is going to be just like a concatenation of small subvectors that are representing the answers under each possible relation. So we have R relations in total. So we are going to have R blocks within the embeddings of each entity. So we are going to have one block for the relation one, and then the second block for relation two, etc. And once we compose these vectors as a concatenation of many components, the MLP is not going to store the information. It's just like going to read the particular relation that we are asking about, and it's going to choose this particular a set of coordinates from the embedding of the entity and get them as the answer. Okay, so like the MLP just like selects the relevant information. It doesn't store anything, and that's why we can have a much smaller MLP. So this is just like a more concrete example. So let's say that we have this particular entity Alice, and we can ask different questions about Alice, right? So what is the identity of her mother, her spouse, her best friend, etc. So we are going to have this particular sets of coordinates VG1, VG2, etc. that correspond to each particular relation. And we are also going to have some embedding for the particular relation that we are asking about in this question, which is going to be the zero vector just with the last coordinate indicating the identity of the relation. So whether it's the mother of relation, the spouse relation, the best friend relation, etc. And once you are going to have all these coordinates, the MLP is just like going to read the last coordinate of the relation embedding that specifies the identity of the relation and choose the particular relevant components in the embeddings of Alice. So this is going to be, as I said, linear in the number of relations and logarithmic in the number of entities. I'll mention that this kind of solution has this nice property that it explains the empirical finding that I mentioned earlier, the fact that you have empirically a linear map between the representation of the subject and the representation of the attribute or the answer for every particular relation. So we have one individual linear map per relation, and you can see it very clearly because the embedding of the subject is just like the concatenation of all entities. If we specify the relation, we have a trivial linear map between the embedding of Alice and the embedding of the attribute. Okay. Are you following so far? Like, is it? I think so. Cool. Okay, so I will not get into it in the interest of time, but you can imagine that once we have this very simple structure in the embeddings, it's not so difficult to design an MLP that, given the identity of the relation, will choose the particular coordinates from the representation of Alice. We propose that one such construction in the MLP. You can come up with alternative constructions based on the attention matrix. It doesn't really matter. The important thing is that the MLP here is very small and it doesn't has to have any storage capacity. It just like chooses a particular set of coordinates. Okay, now it's pretty simple to see that this construction is optimal. So because of simple counting arguments, so we said that each relation specifies a particular bijection. So there are n factorial bijections, and we are going to have R relations. So if we look on every set of R bijections as a particular fact system, we are going to have n factorial to the power of R fact systems. And we have a single factual recall setting. So the model stores given every query subject and relation, it is able to continue with the correct answer, GR of S. So we get that the number of bits in the model must be at least larger than the number of fact systems, so n factorial times to the power of r. Using the Sterling approximation, we get that the number of parameters must be at least Rn log n, which is exactly what we get with this construction. Okay, so this is, so like in terms of the total number of parameters, as I've mentioned, we don't do better from the MLP-based solution, just because you cannot do better asymptotically. But we do better in the sense that most of these parameters are cheap. They're in the input embedding matrix. Okay. Yeah, so this presents the two regimes. So the associative memorization regime, where the facts are stored in the MLP or the attention weights. The embeddings are roughly orthogonal, and the parameter cost in the MLP is linear in number of facts, while in our geometric setting, the fact storage in the geometry of the embedding matrix, the embeddings are more structured, and the dimensionality of the embeddings is going to be linear in R, but logarithmic in N. Okay. If there are no questions, so I continue to the multi-op setting. Is there a question?
Sorry, can you go back to the previous slide for a second? I don't know.
Yeah.
This is the geometric memorization then is built and it's static after it's built?
Yeah.
Or okay, fine. Thanks.
Sure. Okay. So yeah, so this was mainly about the single op setting. Now, what can we do when we generalize it to the multi-op factual recall setting? So we're going to have a k-op query as some subject S and then k relations, and we want to be able to output the compositions applied to a particular subject S. And we're going to present a lower bound argument. So if we do not have access to chain of thought, the model has to zero-shot compose the k relations and return the answer. Then it's very difficult to it's impossible to come up with an efficient solution. So we need to store enough information in the weights to be able to answer any of the possible r to the power of k paths, depending on the k relations that we are going to compose. Or alternatively, we're going to have very large embedding metrics where we store every possible composition in the embedding. And we're going to show that this trade-off is fundamental. So this is just like an illustration of the multi-op case. So we're going to have this like RE tree of depth k, where k is the number of relations that we compose. So for every subject, we have to answer the first relation first, and then we are going to answer the second relation, etc., until we compose all k relations. So this is a very large tree with like r to the power of k leaf nodes. And I'm going to show parts of the proof that we have in the paper for the lower bounds on the number of parameters without chain of thought. So let's say that we have some trained model that is able to answer any k-op factorial recall question on a given set of entities. So we are going to denote the total number of parameters to be w plus n plus r times d, where w is all the parameters of the model that are unrelated to the embedding, so the MLP, the attention, whatever. And then we are going to have n plus r times d bits for the embeddings, okay? Because we're going to have n entities, r relations, we have d bits for each of them, and we have embedding for each entity and for each relation. Now, if we specify a given fact system G, which is just like we specify all the bijections that determine each of the R relations, then we can, if we have a perfect model that is able to solve any k-op question, we are going to be able to reconstruct the fact system by querying the model, right? So we can present the model with every possible k-op question, and get the answer. So the parameters are kind of like lossless code for the fact. Now, if we have b bits in general, they can distinguish to the power of b as entities or objects. So we're going to have a very simple condition that the total number of parameters, w, which is again the number of parameters in the MLP and attention, plus the number of parameters in the embedding matrix, must be at least larger than the logarithm of the number of fact systems that are distinguishable by the answers. Okay, so this is a very simple condition. And then in the next two steps, we are going to count this like a right-hand term, the number of fact systems distinguishable by the answers, in two different ways. So the first one is this kind of like a phone book view, that each relation is like a phone book, right? It's a permutation over the n entities. So each one of them is going to need log n factorial bits, or roughly n log n bits. And we are going to have r of n, so we're going to need rn log n bits. So we need the total number of parameters, the parameters in the MOP and the parameters in the embeddings, to be at least this number. So we are going to get that W, which is the number of parameters in the not in the embedding, in the MOP and the attention, is going to be this quantity, which we call P global, minus all the things that are stored in the embedded matrix, right? So we discount all the things that we can store in the embedded. So this is one bound for the number of non-embedding parameters that we are going to need. And notice that this is when d is small, so the terms rd is negligible compared to b global, then we are going back to the lookup table regime. Well, most of the information is stored in the non-embedding parameters, and the number of non-embedding parameters w is roughly linear in the number of facts. So it's going to be in the order of r times n. Okay, so this was one way to count the number of fact system. Now, the second way is if we focus on a particular entity like Alice, so we can ask r to the power of k questions about Alice, right, corresponding to any composition of r relations. And so we're going to have for each entity an answer list of size r to the power of k times log n bits. Right, and when we ask the question about Alice, the model in the forward pass is only going to see the embedding of Alice. It's not going to see the embeddings of the intermediate answers, like the answer to the first relation in the composition, or the composition of the first two relations, etc. Just because we don't have any chain of thought, the model has to compute the answer directly. So the weights W, the weights that are not part of the embedding matrix, have to absorb the overflow, all the things that we cannot store in the embedding of Alice itself. And it's very easy to see that the number of possible answers, which is goes with like r to the power of k, is much larger than the number of bits that we have in the embedding of Alice. So this gives us, after some like algebra that I will not get into, we get that the number of non-embedding parameters, according to this condition, is at least p, which is the number of possible entities or subjects with unrelated answers list. So like how many kind of like disconnected entities that we can find, times the number of possible answers, which is r to the power of k times log n. And so this gives us a second bound on the number of non-embedding metrics. So we call this b local. And again, we discount rd, which is the number of embeddings parameters. So this gives us this result. So if the transformer is able to solve the k-op task exactly without chain of thought, its non-embedding weights are going to satisfy to at least be larger than the maximum between these two bounds, the b global and b local, minus the number of bits that we can store in the embedding itself. So we are going to get several regimes. So when the dimensionality of the embeddings is small, much smaller than the number of relations, then we are going, as I mentioned, we are going to get back to the like the MLP as a key value memory setting, where most of the information is stored in the MLP, and the MLP is relatively large. When D is between R and R to the power of K, we're going to have some intermediate regime. And when the dimensionality is very large, we have very large embeddings, then we can store all the compositions in the embeddings themselves. Okay, so I hope this was not too obscure. Any question? Okay. Now, it's intuitively very easy to see that chain of thought can easily break this lower bound, right? Because if we have the ability to generate intermediate answers, so our chain of thought is just going to be the answer to the first relation, then after we generated the answer to the first relation, we can just apply the second relation on this intermediate entity, etc. So we have the chain of thought which is just the series of intermediate answers to the composition of every prefix in the sequence of k relations. Then, after we generated each intermediate answer, we can read it, and we can read the embedding of this entity, and then we can easily compute the answer to the next relation. So we are just going to sequentially apply the efficient solution that I showed for the k=1 situation. And this application is just enabled only with chain of thought, where the model can read the embedding of the intermediate answers that it computed. So with chain of thought, we are getting back to the very simple, very efficient very efficient solution for k=1. And the number of parameters is not going to depend on the number of relations that we compose on k. Okay, so we're going to get a linear embedding width. Okay, so and there is some machinery in the proof, but I think the intuition is very clear, and we find that with chain of thought, KO factor recall becomes almost like trivial. So this is just like a table summarizing the different regimes with and without chain of thought. And I think in the interest of time, I'll continue to the more like experimental part of the paper. Sorry. Yeah. Okay. So far we had a theory on like a simplified sequence structure and a very simple ML transformer with single layer, and now we are going to see whether gradient descent is actually converging to something similar. Yeah, so we specify some number of entities, and we try different number of relations and different dimensionality. And we're going to train at first a single layer transformer with uniform attention and standard MLP model. Okay, so first we find this. Here we see on the x-axis of each of the two figures the dimensionality of the model, and on the y-axis the number of relations that we trained with. On the left we have our setting with trainable embeddings, and on the right we have the original setting with frozen embeddings. And you can see that the trainable embedding solution is much more efficient. So the numbers are the accuracy, the final accuracy of a transformer trained with this particular data. And we can see that with trainable embeddings, once D is large enough, we almost always get perfect accuracy, while the model with frozen embeddings needs much higher dimensionality in order to store all the information. We can also see it in the this kind of like asymptotic plot. So here, for each value of n on the x-axis, the number of entities, we lowered the dimensionality until we got to a point where the model can no longer memorize. So we record the minimal d that can still memorize all the set of all facts. And we find that with frozen embeddings, we have this squared root dependency. So like the width of the MLP is going to be the square root of the number of facts, right? Because the total numbers of the parameters of the MLP is going to be linear in the number of facts. While with trainable embeddings, we get this logarithmic dependency on n, the number of entities. This is the blue curve. Okay, now, okay, so we find that indeed, like trainable embeddings is better in terms of efficiency, but the question is whether the model is actually converged to something similar to our particular construction. Maybe there are other constructions with trainable embeddings. So one particular signature of our construction is that we are going to have this like linear dependency between the representation, the uncontextualized representation of the subject and the representation of the answer for every particular relation R, right? Because if the embedding of the entity is just a concatenation of components that correspond to every particular answer, it's very easy to read out the answer from the uncontextualized embedding of the subject. So we try just that. We fit this kind of like ridge regression. And indeed, we find that it's possible to decode with perfect accuracy each answer from the uncontextualized embedding. And this is not the case with frozen embedding. So if you, I don't show it here, but if we repeat the same experiment with frozen embeddings, we are having almost random accuracy. So you cannot decode the answer. So this is one like supporting evidence. Any question? Okay, so this is nice, but this is not enough. We can do better. So one particular property of our construction is that the MLP doesn't store anything, right? It just like selects the particular, the relevant component from the embedding. And if this is true, we should be able to keep the MLP frozen, update the facts by just like changing the embedding metrics without changing the MLP. And the model should be able to perform zero shot with high accuracy. So what we do here, we just like sample a new answer for a particular entity. So instead of like specifying Marie Curie's occupation as chemist, we specify it as something else. And then using very simple linear algebra and using this like readout metrics that we fitted earlier, WR, we can compute what is the minimal norm update to the embedding metrics that will change the answer for this particular relation. So we change the embedding metrics, but we do not change the MLP at all. And then we compute this selectivity metric, which is some like geometric mean of two conditions. One, we want the model now to produce the new answer when queried. And the second, we don't want to damage the answers under different relations, which we didn't manipulate. So this is what you see in the plot to the right. So like the y-axis is this selectivity score, where higher is better. And indeed, we find that like above certain dimensionality, we get almost perfect selectivity. So we are able to update the fact system without changing the MLP at all, showing that the MLP probably doesn't store anything. It just like selects something from the embeddings. And we can take even a stronger version of this experiment, where again, we freeze the MLP, and we sample a completely new set of bijections GR prime instead of the original bijection GR. So we have the same set of entities, but for each relation, we sample a completely new mapping between entities and answers. And again, we don't change the MLP at all. We compute the linear update to the embedding metrics. And then we query the model again with the new set of the new fact system. And this is what we see on the heat map on the right. So different dimensionalities on the x-axis, different number of relations on the y-axis. And again, with high enough dimensionality, we are able to get almost like perfect zero-shot accuracy without updating the MLP at all. So this shouldn't be possible if the MLP itself is storing information. We also run some experiments on chain of thought, and this is the result here are aligning with our theoretical construction. So if we do not have chain of thought, or if we have chain of thought but with frozen embeddings that are not trainable, we struggle when we compose enough relations. While on the right upper heat map, if we have chain of thought and trainable embeddings, we get perfect accuracy regardless of the number of facts that we compose. Okay, this is most of the content. The last part is going to be about actual, like trainable language models. Any questions so far? Okay. So just like to summarize, so far we presented this theoretical construction and we showed that if we train a very simple transformer with gradient descent, we actually converge to a solution corresponding to our construction. But now the question is what's happening with real language models where we have multiple layers, we are going to have much more much richer data structure with like semantics and paraphrases, etc. So we cannot really hope that our clean construction is going to be replicated in real models, so there is no reason to store all the information in the embeddings when you have so many MOP parameters. Probably what we have in practice is some kind of combination between the two idealized regimes. So some of the information is going to be stored in the embeddings, and some of it is going to be stored in the MLPs. And we try to kind of like quantify this or see whether we see some signatures to embedding-based memorization in real language models. So we experiment with several language models and several factual relations. And in the experiments, we're going to try to linearly decode the information about the answer from the representation of the subject in different layers. So first in the unembedding layer, or sorry, the embedding layer, like the first layer, and then in the contextualized intermediate layers. So these are the results. So we see on the y-axis different kinds of factual relations, and the metric is some kind of like one particular way to quantify the ability to linearly decode the answer from the embedding of the subject. This is not on the input embedding layer. This is on some like relatively early intermediate layers. So this doesn't directly correspond to our construction, which focused on memorization that only happens in the embedding layer, but still it shows that there is this like linear signal that is coming either from the embedding metrics or from at least like the early contextualized layers. We also get some like non-trivial decoding ability based on the input embedding layers, but it becomes much better when we do take into account several contextualized layers. So we do get representations that linearly encode the different answers under different factual relations, which is largely consistent with our construction, even if it doesn't like neatly align with it. Okay, so there are some limitations of this approach. So of course, like in real language models, we have correlated factual relations, we have semantics, we have semantic types, etc. All these things that we ignored in our theoretical constructions. And intuitively, the geometry or like the learned embeddings should reflect at least some of these factors because they are useful. And our construction doesn't take this into account. Again, there's the question of what's really happening in pre-trained language models where you do have intermediate layers. So how does the model choose to partition the information between the input embeddings and the MOP parameters? And there are some like gaps in the theoretical constructions, but I think this is maybe like less interesting or important right now. So the takeaways. So we showed that learnable embeddings change the capacity store, so we can have relatively small embeddings and store the set of n times r factual associations. the mechanism here is geometric, so the subject embedding to have this particular structure where we have components corresponding to every possible attribute, and the MOP is just like a generic relation-independent selector that, given a particular relation, chooses the particular coordinates. In multi-app questions, we showed this trade-off, where without chain of thought, you either have to have many MLP parameters or to have very large embeddings. But with chain of thought, we can go back to the efficient k=1 solution. And at least in toy data, random descent favors this geometric construction over the classical MLP-based construction. As final remarks, I will mention that this may hint towards a more general phenomenon. So there is a recent paper that demonstrated that when you train a transformer from scratch on graph structure, so kind of like language modeling on graphs, you get embeddings that reflect the geometry of the graph. So this is what you see on the right when you train the model with trainable embeddings. You get embeddings that reflect the particular geometry that you trained on. Our analysis can be seen as kind of like a special case of this because factual recall, at least in our simple toy setting, is inducing a particular bipartite graph with edges corresponding to the associations between the entities and the answers. So the question is whether we can generalize this to a more to any arbitrary graphs beyond this particular graph structure that correspond to factual recall in our analysis. So this is something that I've been trying to think about recently. That's it. Thank you.